Hi, my name is Leo Rivera. I'm the Director of Scientific Outreach here at Meter Group. And today we're going to talk about soil moisture release curves and some of the best practices behind getting good measurements. One of the first things I like to start with when it comes to best practices for getting good measurements is really trying to think about which properties are most critical, because these are some of the things that might govern how you approach your measurements and which things you decide to focus on. The first important piece to think about is what is the range of water potential that is critical. In past videos, I talked about how the instruments have range limitations, and you can see kind of what that looks like here. But in some cases, if you're only focused on the wet end of the soil moisture release curve, then you're going to just focus on really getting good measurements with one tool, because in some cases, for example, you can see here a sandy soil that most of the water is held in the very wet end of the soil moisture release curve. So for the most part, we don't really need to make that dry end of the soil moisture release curve measurement to really understand what's happening there. We can just use the retention curve and fit the rest of the data there to really understand what's happening. But for our finer textured soils like the silt loam curve that we see here, there is still quite a bit happening in the dry end of the soil moisture release curve that we can't measure with just one device. So that's a case where we're going to need to make measurements with both devices to get a good soil moisture release curve. Again, some of it comes down to the coarse versus fine textured soils. Soilless media, oftentimes we can get away with just the wet end of the soil moisture release curve, versus mineral soils. Oftentimes we're going to need to get both the wet end and dry end measurements of the soil moisture release curve. And especially for mineral soils, there's a lot more information in the dry end of the soil moisture release curve that can help us understand some of those fundamental properties. Another key point to think about when it comes to best practices for measurements is accounting for hysteresis. Hysteresis is something that exists in soils. It changes with wetting and drying curves depending on what that looks like. And we need to understand that, and we really need to understand how the measurement device that we're using is working. Is that device working on a drying curve? Is it working on a wetting curve? Can it do both? For example, the evaporation method only works on the drying curve. And so that we need to understand that, especially if we're trying to combine that with something like the vapor pressure methods like the WP4C, which we do those manually, and we can do both wetting and drying curves. If we're trying to combine the two measurements together, we're going to want to make sure that both measurements are being done on a drying curve. And I'll talk a little bit more about approaches that really help simplify how we make those measurements with the two devices together. One other important thing when it comes to best practices for measurements is, again, understanding the limitations of the sample that we're actually taking, right? So typically we're trying to characterize a full soil profile and what's actually happening in that soil profile with most of these measurements. But one issue with that is our lab measurement is a single point assessment. We're just taking a core from within that profile and trying to measure the properties that represent that whole profile. So what that really means is we're going to need to measure enough samples to actually properly characterize that soil profile. I've talked about best practices that can be utilized in any measurement device when it comes to measuring soil moisture release curves. Now I'm really going to focus on how to best utilize the Labros tools to do full characterization and fully measure the soil moisture release curve. And again, that first point that we need to focus on when using the HYPROP and WP4C together is that we need to account for hysteresis. And that means we need to make sure that both of our measurements are on the drying curve. Again, that evaporation method primarily operates on the drying curve, and we can do both with the vapor pressure methods, but we want to make sure that our vapor pressure method measurements are on the drying curve. And the best way to do that is to actually directly subsample from your HYPROP sample to make your WP4C measurements or your vapor pressure measurements. And so the best way you can do that is after finishing a HYPROP measurement, what you do is you actually take that core, and what's nice is the core is going to have a gradient of water content because of the way the evaporation method works. We're evaporating from only the surface of the core. That surface is going to wind up being drier than the deeper sections of the core. So that means we have samples within the core that are going to be at different water contents that are already on that same drying curve. And so what we can do is subsample from that core by subsampling first from both the top and the bottom of the core. When we pull that core off, we can take subsamples and put them into the sample cups for the WP4C. And then we can actually sample from the intersections of the sample. I typically like to sample at 3 interpoints. So essentially at the first quarter, the half, and the third quarter point within the core. And what that does is that gives you a nice range of samples that are already on that same drying curve and typically cover the range that you need to cover the rest of the soil moisture release curve for that sample. So now that we've made all of our measurements with the HYPROP and the WP4C, another key point when trying to combine the measurements is accounting for the matric and osmotic components of water potential. So one challenge when combining measurements from the HYPROP and the WP4C is the HYPROP measures matric potential. The WP4C can measure both matric and osmotic potential together depending on how many solutes are in the soil. So what we have to do is we actually have to correct for the osmotic potential from the WP4C measurements by actually measuring the saturated extract EC of the sample and then combining some simple models to actually help us separate out the osmotic component from the WP4C measurement so we can better combine that with the HYPROP. Now, this is not something we're always going to have to do. It's typically in more saline soils where we're going to have to make this correction. But you'll often know when you combine the measurements, if the HYPROP measurements don't overlap well with the WP4C measurements, typically you're going to see the WP4C measurements read a little bit higher as they get closer to the wet end. Then that means we need to look at doing an osmotic potential correction. So now that we have all the measurements we need to generate the soil moisture release curve, the next step is choosing the right model. And just like the instruments have evolved over time, the models have evolved as well. We all are familiar with the traditional Van Geneuchten equations for fitting the soil moisture release curves. There's also the Brooks and Corey and the Campbell-Shiozawa model. These models have all evolved over time, and especially as we've learned more about what the soil moisture release curves actually look like. And so I think one last important piece when it comes to best practices for generating soil moisture release curves is choosing the right model to fit those data. Another important part is, does that curve show bimodal characteristics like you see here? Then we need to make sure we're choosing a model that properly fits a bimodal curve. One other important piece when it comes to looking at these models is theta R really still relevant? And I would argue that it's not. As we've learned more about the soil moisture release curves and what the drying of the soil moisture release curve looks like, we see that there isn't a true theta R. The soil can actually dry to a true zero water content. So we need to use some of the models that can better represent that and fit what those data actually look like to have a good fitting of our soil moisture release curve. Newer equations like the PDI variance of the Van Geneuchten equation and some of these other models help better account for that. The Friedland-Jing model also does a better job of accounting for the way the drying of the soil moisture release curve looks. One other challenging piece of this, of course, though, is the complexity of the model. As we start adding these pieces that help the models fit the curves better, they sometimes become more complex in terms of mathematics, which can make them harder to use in some cases. So you want to make sure that you have the ability to use the more complex models and the tools that you're trying to actually use the data for. So I've talked about some of the best practices behind making soil moisture release curve measurements, but there are a lot of other things that you need to think about and other best practices around making those measurements. So I encourage you to check out some of our other educational content, including webinars and other videos about water potential and making soil moisture release curve measurements.